So Professor Satya Sahoo is a professor in the Department of Population Quantitative Health Sciences, School of Medicine, and then he has a bunch of other affiliations: Director, Biomedical and Health Informatics PhD program, Associate Professor of Neurology, Department of Neurology, and also associated with Computer Science and Engineering, and also with electrical computer systems and so on and so forth, or Cleveland Institute of Computational Biology. So Satya did his PhD from Rice State University, and and he joined Case Western Reserve University. Uh, Cleveland Clinic is a major medical establishment there. His PhD was in computer science, but he did a lot of work with people in complex carbohydrate and other life science researchers. He was very involved in developing a provenance model for provenance. Where does the information come from? That is a very important thing to know, also called grounding these days. And he had worked with he developed an ontology called provenance that eventually become helped develop an international standard from worldwide consortium on provenance. He in a way continues the work around his knowledge representation and reasoning, and along with machine learning, and applies that to various issue in neuroscience. So there is a long resume here, but it's more than 5,000 citations to his work, and has done very well in developing a very internationally, very interdisciplinary research program that has become, yeah, that's been well funded and has been impactful. So take over, Satya.
Thank you, Dr. Can you hear me now?
Yeah.
Okay, and you can see my screen?
Yes.
Okay, great. Thank you, Dr. for the introduction. I would like to note that I have three of my PhD students also joining in. Pedram Golnari, he's MD by training from Iran, and now doing his PhD in biomedical health informatics in my group. Deepak Upadhyay, he is in the fifth year of his PhD, soon to graduate. He has a background in health epidemiology from Nepal. And lastly, but not least, Katrina Pranzolas. She is also in the fifth year of PhD in epidemiology and biostatistics. I think her thesis focus is more on informatics rather than epidemiology, but she was admitted to the epidemiology biostatistics PhD program. Interestingly, we have three PhD programs in our department. One is BHI, Biomedical Health Informatics, one is Epidemiology Biostatistics, and one Clinical Translational Research. And her thesis work is in brain network dynamics. It's wonderful to be here. I can't see the audience, but I'm sure during Q&A I'll be able to see all of you. Today, because of the time limitation, I'm going to focus on one of the applications that we are working in our group. And I sort of came up with, oh, okay, that's helpful. Okay. And maybe the, yeah, great. Okay. I can see everybody now. So it's been quite some time. I used to sit on that kind of a chair. I remember quite some time ago during my doctoral research. So without further ado, as Dr. Shid mentioned, I have had a long history in knowledge representation, the sort of unsung component of AI. But over the past 3 to 4 years, I have moved into the learning models. And what we have discovered is that these traditionally two sort of separate camps in AI in certain ways can be merged and have complementary strengths. that have a lot of applications in medical research or broadly in biomedical research. So I don't have any conflict of interest that's relevant to this presentation, except that Dr. Shet is my advisor, PhD advisor. So all of you have been working in LLMs, I'm sure. It's a flavor of the season. And what I wanted to point out today is all of you have used different kinds of prompting. Many of you have publications. I know many of Dr. students have also been extensively using language model in a variety of applications. Since Gemini 1. Actually 1 and 1.5, there has been this trend towards increasing from what GPT-3 started to Gemini Pro, which was 32,000 context tokens, to GPT-4 Claude, and now, of course, it's more than this video from Google research shows up to 10 million tokens with more the recent Gemini models and the GPT-5 models. And that translates to 1 hour of video, 11 hours of audio, significantly large context size. But then the question arises is, with primarily, there has been this discussion about what works better. Do you fine tune a model for very niche applications in medical applications primarily, or can you achieve similar results with prompt tuning? And there was this very influential paper from Microsoft Research in 2024 by Nori et al., who showed that at least with the US medical language examination questions, just with prompt tuning, you could achieve better results than fine-tuned models like MedPalm, which was at that point from Google DeepMind, was setting the benchmark performance over USMLE questions. So in our group, what we have been looking at is, given this long context models, um, do we discard the notion that you don't need to worry about prompt tuning per se? You can just give 1 hour of video. I'm sure with 10 million you can have 6 hours of video and so on. Do you need to even think about prompting appropriately? And if you see here, this is a recent paper that talks about in-context learning with long context models by Bursch et al. From CMU. You can clearly see the number of examples is going up to 10,000 examples, and they're reaching accuracy over TREC. Many of you would be familiar with a text retrieval benchmark, natural language understanding benchmark. Banking 77 is another benchmark that has about 13,000 um, customer query answering examples, and Clinic is another benchmark data set for customer intent, and they're achieving nearly 90% accuracy. But as you can see, the context size increases from about 10 to 10,000 or greater numbers. All good, but then, and this is actually the table from the paper I took, that getting up to 14,732 examples in the context learning, the context window, and for TREC they go up to 5,000. Now, if you take a step back and think about this, what are the computational costs for this? And interestingly, just recently from NVIDIA, they had this blog post sort of take on a new approach. They're calling it NEMO, where they're talking about what are the costs of scaling to this millions of context size windows, and they charted the complexity in terms of big O. There's a square increase as the context size increases. There's a complexity of O n square. And they made a very telling note there, and this is from NVIDIA, that this context size, especially in the GPU context, won't even fit in a single GPU, even the latest state-of-the-art GPU. And memory management becomes very expensive. So many of you would be in computer science programs. My background was in computer science. So this is an interesting note that even in the long context models, ICL has its downsides. And if I put my other hat on, in medical applications, there are many practical considerations. Uh, in many cases, you have small cohort. You don't have a large enough cohort to actually have 14,000 examples, as we saw in the previous table. Rare diseases, by definition, you will have to maybe up to 100, if not less, number of examples to use in your in context learning. And when you have longitudinal data, you have a lot of missing information. There are patients who drop out, and there's attrition. There will be certain adverse events that are occurring in studies. In our group, we deal with Parkinson's disorder. There's a very well-known study from the Michael J. Fox Foundation where they were tracking patients. So these are very practical considerations when you think about using in-context learning to get good accuracy, which clearly will not work with the kind of approach that's been discussed with 14,000 or 5,000 examples. Given that, um, what are the solutions that we can come up to adopt these long context models without having to use extremely large ICL data sets? I'll use one example to sort of drill down in all these issues that I have brought up. And I should mention, please stop me if you have questions. Happy to, I want this to be more of an interaction rather than just a dry presentation. So please feel free to stop me at any time you have questions. I'm going to use this example. We have been working in epilepsy for past 14 years now, 15 years. I'm going to take an example here led by Pedram and Katrina in a rare pediatric epilepsy called Dravet syndrome. And there is a key question, research question that is trying, and in broader clinical research, this question comes up multiple times. If you look at, you have model systems. This is a zebrafish. You have maybe cellular components, mouse models. How do these models actually translate to effectiveness in human conditions? This is very pertinent questions in the broader context also, because we know that many of these drug development cycles, which involve phase 1, phase 2 successful results, are failing in phase 3 when they go to clinical trials or in human evaluations. And these are expensive clinical trials. There are 10 billion to 20 billion that are invested by drug companies. So this key question, how do we understand which of the models that we develop, and these are these are genetically modified mouse models or genetically modified zebrafish models, whatever are the discoveries, how they translate to human conditions. And in case of Dravet syndrome, which affects children primarily, you can have, and this was identified by our clinical domain expert, collaborator Dr. Jeff Buchalter. He divided it into 9 broad dimensions: genetics, development, behavior, pharmacology, seizures, electrophysiology, and the effectiveness of any of these drugs. So our attempt when we started this project with funding from the Dravet Syndrome Foundation, the question we are trying to answer is, if you take certain number of, let's say, anti-seizure medications, here is a list of these very well-known and widely used medication information, and we know about their effectiveness both in humans as well as in model organisms. So you have patients, you have particular type SCN1A lab, SCN1 lab zebrafish is a particular variant of that, and you have SCN1 lab MO zebrafish, another variant of that, and you have Dravet syndrome variant of mice. And This is from a paper from 2017 by Griffin et al., some of the experts in Dravet syndrome. They manually reviewed 10 publications that you see at the bottom of this table and created this table to compare the effectiveness of what they found for these set of anti-seizure medications. So these are experts, they manually reviewed the studies and they built this table. And what's important here is the effectiveness when you administer these drugs, are they reducing the seizures? But there has been a lot of discussion in the epilepsy community and in specifically in Dravet syndrome. In these animal models, the seizure, when these humans or model systems experience seizure, they can be spontaneous, they happen on their own, or they can be induced. And many of you might know that there are, when you watch some videos, there is a warning that some of the children might be photosensitive. So they might have this because of some flashing lights and things like that in movies, children might have seizures. Hyperthermia. So when you put these models in very high temperature, then they start having seizures. And we also know that in children, when they have very high fever, they have seizures. That's why one of the key aspects of in children is that making sure that the temperature when they have fever doesn't go above a particular threshold. So this differentiation, as you can see, we are talking about um, the particular medication information, the organism, the effectiveness information, and the trigger. So effectiveness in the context of whether they were able to reduce, these medications were able to reduce seizures when the seizure happened on their own versus when they were induced by light or by temperature. What's interesting here, you will see the effectiveness, whether valproate, for example, was effective in patients. They actually link to particular studies. So you have the provenance link here of where they are getting this information. And in this case, this table, of course, is being was created after reading these papers by these um, Dravet syndrome experts who would be able to interpret the results, right? So you can see here, for example, stiripentol was not effective in this particular model, zebrafish, both for spontaneous seizures as well as temperature-induced seizures. But it was effective in zebrafish who had spontaneous seizures, for this particular model. Very interesting difference in effectiveness. And you also see that this drug is also effective in humans. Our objective was, given this information and given this 10 full text articles, can we recreate this? Because this actually took a lot of time, as all of you can imagine, and you try to expand that to, there are about 400 publications related to Dravet syndrome. If you're trying to do, extract this information, um, it's almost impossible for humans to read through those 400 full text articles and try to gather this information and try and answer the question that we saw in the previous slide, which of the drugs are actually effective across model systems and human conditions, right? So our objective was, can we use language models, especially these long context language models, to recreate this table automatically? So what did we do? We went to the language model and asked it, right? So can you extract these set of anti-seizure medications, the organisms, the triggers for the seizure, and the effectiveness information? And you can clearly see here the results were more than disappointing, right? So 35% accuracy, 29% accuracy, 55% accuracy, it's actually lower accuracy than a flip of a coin. In effect, there is not even a equivalent performance to random chance. So this is using, I believe it was from Gemini 1.0. Pedram can correct me if I'm wrong,
So,
right?
Satya, I have a question.
Sure.
I work with a company. That company does coding, medical coding of electronic EMR documents. Um, and they found that Gemini does far better than other models. In coding, you have this ICD-10 coding and things of that nature, right? And a conjecture is that Google has invested a lot in developing health knowledge graph. Basically on Google, 5% of the queries are health-related queries. Now you probably know that Google uses health knowledge graph. Something called Google knowledge graph, which is all kind of entities and um, relationships that are there. Suppose you have a person, let's say Barack Obama, in Wikipedia, then that is an entity, Barack Obama. He is a politician, past president. All that information is there, right? And that is part of the knowledge graph. Okay? Now, because that knowledge is symbolic, very clear, when Google combines with its query that may use machine learning, then the results are better when the knowledge graph has additional information associated with that. Now, the similar things is what we think we observed with the large language models, where we believe that because so they have two knowledge graph. One is general knowledge graph, one health. And for 95% of the query, they use general knowledge graph. For 5% of the health query, they use health knowledge graph. Now, because they have health knowledge graph, which does have all this medical coding and other information, we are assuming that they used this knowledge graph during the training. That means this particular language model training involve, the medical knowledge, appropriate coding knowledge at the training side as time. And we have observed that what the language models learn during the training is far more, is something that models pay a lot more emphasis on than what we try to do post training. So Gemini gives very good result because it was trained on this particular knowledge, and the others don't do as well. They do fine, but not as well as Google's language models. In here, in this case, is it possible or that I mean the literature you're talking about here of epilepsy and scientific literature is a not a common information. It may not have been part of the web crawl that on which the language model get trained. So if conjecture is that if they had taken these publications, some of them may be under the paywall, and included in the training, they would have performed better than. But if they never, this uh, uh, you know literature also have symbols and coding and formula that are not plain text, and so there's not a lot of supporting material for the language models to understand. Don't have many examples of anything. So here you are exposing them to various terms and symbols and uh, medical specific facts. Then it may not do very well. Um, is that something that is possible, or what is your take on that?
Couple of points. So, first is, of course, there's a debate in the language model community whether fine tuning is the better approach than prompt tuning. And without getting into that, what we have seen is that we have sort of exploring both the approaches. Prompt tuning, when it comes to very niche applications, especially in medicine, which is very complicated, and Dr. Shet also knows from Karthik Ramakrishnan. He was in the lab and graduated a long time ago. A medical text, by definition, is very complex. There are dependencies across sentences, across pages, and so on. And the terminology, as you correctly mentioned, is very, very specialized. So to expect, even if they are using health knowledge graph, to be able to use or be aware of the terminology, let's say with Dravet syndrome or epilepsy, would be low. The probability would be very low.
Yeah.
So not very surprising to see this kind of a result. Also, I should note here that this prompt that Pedram used had the complete question in one prompt. So the question was, can you recreate this table using this full text articles, 10 full text articles? So in the next step, what of course we did, and now we know that you can actually phased prompting. So you break down the components of your prompt, let's say to drugs, to organisms, to triggers. It's and you ask questions specific to those components. Clearly, you will see that as compared to the previous one, where you have 29%, 30% for ASMs, it goes up to at least 63%, 57%. So there are prompt engineering techniques together with in context learning that you can improve it further. Does that answer the question? Or
Yeah, the
yeah.
main question was about um, doing the special effort to in the language model training itself to understand and consume and be trained on specialized information that here it would have. uh, the lack of adequate coverage of specialized, the different corners. So the general purpose thing that you can find online versus specialized things you don't find online as easily. I mean, they are online, but they are not necessarily, part of the general literature or news or other things. And there you need to put special effort to ensure that you can that content is there at the training time, that there is a particular metadata or knowledge graph that I use in training that, or that they are done for fine tuning, or they are done at the time of prompting and context engineering. So there are multiple different ways that you can influence,
Yeah.
but the effort that you have to do post training is much higher in the problems that you solve,
Yes.
and whether it will be good to train a model, a specialized custom model. One of the areas we work on is so we call now a custom compact neurosymbolic AI models. So we work towards creating a specialized enterprise class models, not the large language models. And I'm just wondering that for specialized problem, perhaps doing research and developing specialized models would be better than using large language models. And that could be very exciting, unique research approach.
Yeah, so I'm glad that is quick question. So to answer the question, yes, we don't need to do fine tuning. We can actually use knowledge models
Hmm.
to build, to take any of these generically pre-trained models and customize it to very, very niche applications. So, and that's what we did. We actually took an ontology that we have been working on for the past 15 years in epilepsy and use that to augment this prompting approach that I just described, Vedant came up with. And then we were able to integrate that in our the prompt expressions. In effect, if you look at it, so this was the baseline prompt. We asked the question straight away. Then we applied the different phases that the phased in context learning. And then we augmented it with the ontology. And I'm going to dive deeper into that because I think this audience would appreciate the use of the ontologies as knowledge models. So broadly, we have all the medication information, the stimulus information, as I just mentioned, whether it was light induced, whether it's auditory or temperature induced, and use that to to try and recreate that. And what you see here across the four different categories I had mentioned earlier, for the 10 papers, it got 100% accuracy. It was able to retrieve all the medication information, all the organisms correctly, the effectiveness information correctly, and most, significantly, the trigger. The trigger, as I mentioned, if I go back to my slide, earlier slide, the trigger is extremely difficult to extract from literature. And many of us who have done work in natural language processing and text retrieval would know being able to differentiate the effectiveness of, let's say, valproate in spontaneous seizure versus hyperthermia-induced seizure, or let's say in terms of the primed differentiating between spontaneous and primed spontaneous in mice is extremely difficult. And it's remarkable that the effectiveness goes from 29% for effectiveness and the trigger and the name of the medication, the ASMs, goes up to 100%, as you can see here, across all of them using the ontology. So effectively, we were able to recreate what the medical experts, the Dravet syndrome experts had done manually over months of reading these 10 papers and extracting and making sure they had the correct information. The model is able to recreate that using the ontology as a knowledge model. And going back to the original question I had asked, can we, how do, does quantity, do you need 14,000 examples to do in context learning for this long context models to achieve these results? In fact, Pedram actually did the experiment, and he found with just two examples, the model reached 100% accuracy across all four components. That is being able to differentiate between the seizure trigger, the anti-seizure medication information, the whether it's human or if it's preclinical model system, and the efficacy information with just two examples. In effect, from a practical consideration, we show in a rare condition, you don't need 14,000 examples, 5,000 examples, or whatever that is. Even with two examples, that's augmented by a knowledge model, expert curated knowledge model, an ontology, it got 100% effectiveness. And Pedram actually extended this further. What he showed was even if you keep increasing with the baseline and the phase in context learning approaches, with 10 shots also, for ASMs, it could not go above 60%. For, let's say, organism name, it could not go above 80% or 90%. Similarly, for the trigger information, similarly for effectiveness, which is continues to be low in the low 40s, 50s, which is most complex, of course, information, it's not able to go above, even with very sophisticated, phase in context learning. But with the ontology, just with two shots, it's able to reach 100% accuracy.
Dr. Sahoo,
Sure.
is that do you have that example, or are you going to show it in the further slides? That augmented ontology augmented prompt.
Um, could you repeat your question, please?
So I'm just trying to see that do you have an example of an ontology augmented prompt?
Oh, the
Because
prompt expression.
yes, yes.
Yes. So I was in a bit of a rush to create these slides. I'll put our link to our webpage, and I'll put the contact information for Pedram. We just had a paper. Pedram was the first author published in International Journal of Medical Informatics that has the prompt expression. So I would refer you to the paper which has additional details.
Thank you.
Other questions?
Yeah, I have one more. So after you build something like this, are you trying to provide this to doctors or to patients? What is your goal
What are the
after?
next steps?
Yes.
Good question. Okay, so before I get to that, let me actually, because all of you would appreciate this, what's the secret sauce, right? So I'll do a little bit of a deep dive into what this knowledge model that does the trick of with just two shots get 100% accuracy. So this is the epilepsy and seizure ontology. It's freely available on Bioportal. It has about 2,000 classes, as you can see here. And we have very detailed level of modeling of information. We have spent, as I said, 14 years, 15 years working with clinicians trying to incorporate this information. And what you would appreciate, especially this audience, why I'm going to go through this has all the ingredients of creating a very high quality knowledge graph. about Dravet syndrome or broadly about epilepsy. So it has information, for example, age of onset. What were the associated disorders associated with Dravet syndrome? What kind of mutation happens? It happens in SCN1A. What are the specific EEG variations? What are the preferred medication information? In terms of genetic, a particular gene mutation that is overwhelmingly responsible for occurrence of Dravet syndrome in children, you have information that this gene has sequence variants. These are all the different variants. And further, these different variants are linked to the ClinVar database, and you have linkages here that talks about the molecular, what kind of variant is it? It's a missense. There are variant types, single nucleotide variant, and what are the phenotypes associated with it. As you can see, in addition to Dravet syndrome, mutations in SCN1A are related with generalized epilepsy with febrile seizures, in early infantile epileptic encephalopathy with suppression bursts. These are various types of disorders, and these are all linked. I am jumping from the variant to the variant's phenotype. You can also see in terms of the missense variant, this is linked to the sequence ontology, which is part of the gene ontology. You also have location, anatomical information in terms of what is it responsible for. So this was actually put together by Katrina by working with the Dravet syndrome experts. She collected all this information and structured that they could be modeled in the ontology. And I can go on and on in terms of the focal cortical, the different kinds of malformations that are associated with it, the particular neuropathologic findings. As you can see here, very detailed level of modeling has been done. I'll stop at this point, going right up to the particular part of the brain where the particular sclerosis happens. And you can see here, and I'm sure all of you have done in your coursework, this is just using the OWL expressions. And this exactly replicates the information that medical experts, clinicians have added to text, published in papers, but this is all being structured here. And those of you who, all of us keep hearing this term knowledge graph, if you have been keeping track across these last 7 slides, all of them form a knowledge graph, because these are not just list of terms. This is not a subsumption class hierarchy. These are all linked together by named relationships. Has astrogliosis value, is located as, has, fibrillary astrogliosis. That forms the component of a knowledge graph. So if you take a step back, going back to what Dr. Shet mentioned, so Gemini or even GPT, they are using these variations of schema.org or any of these other knowledge graph representations. Here is an example of a very niche knowledge graph that significantly augments the performance of a language model in very complex tasks. Please stop me if you have questions. So going further, of course, Pedram expanded this study from 10 papers to all. There are about 4,900 articles. Now there are more. This is from last year, April 2024. And he was able to expand the corpus from the previous 10, when the original paper was published, to 75 papers. And he was able to create, I'm not going to get into the details of this table, but as you can see, effectiveness and not effectiveness for the same set of medication. What's most important, takeaway from this table is he identified gaps in current knowledge. He also identified studies that had conflicting reports. So, for example, valproate was found to be effective by one study in a mouse model, but not effective in another study, right? And similarly, you can see here for clobazam, one study found it to be effective, another study found it to be not effective. For another medication here, stiripentol, there is no information out there. So what this helps to, what's the value of this? What's the practical value of this? For clinicians, it says if there are clinical trials going to be conducted from model system data, you have to look here and potentially reconcile if somebody wants to do the effectiveness of valproate from mouse model, you say there are two conflicting results. That has to be reconciled first before you actually go on to a clinical, human clinical trial phase. Or you say for basic scientists, what is the gap in information? There is no information about clonazepam with respect to unprovoked seizures in mouse models. So there's a gap in knowledge. So this is hypothesis formulation. So you can generalize this information using this kind of an approach, doing text retrieval, knowledge, natural language understanding, actually I would say medical language understanding, and have impact on clinical research, clinical practice, as well as basic science research. And taking this further, Pedram is developing this practical tool that the Dravet syndrome community can, instead of having to, go to PubMed and trying to see what is the latest publication, they are able to get this structured information along any of the 9 axes that I had shown in my previous slide: electrophysiology or development, sudden unexpected death in epilepsy, SUDEP, drug responsiveness, seizures, and so on and so forth. Okay, I'm going to switch gears. I don't have a lot of time. I know it's already 3 o'clock. There are other studies that, for example, Deepak has done where he has been able to structure medical expert input. This is in collaboration with Cleveland Clinic here for pediatric ophthalmology for early detection of amblyopia in children, and he was able to prompt engineer the language model. I believe both GPT, Deepak, right? GPT and Gemini.
Yeah.
Yeah. So that they were able to significantly improve the performance in terms of accuracy for these children, for this data set. And also, there's another project that is led by Katrina, and who is using clinical phenotypic similarity that are detected automatically by these language models to detect aberrant brain interactions in epilepsy. And she is, especially very creatively has been integrating a branch of pure mathematics called algebraic topology with neurological neuroscience, neurology, and Gen AI model. So this was a recent paper from EMEA 2024, where she was trying to use similarity of patients to for in context learning for seizure prediction. So being able to differentiate when a patient is having seizure or not having seizure. Now, of course, she is also looking at surgical outcomes, predicting surgical outcomes for these patients. And finally, I just like to pitch in. We just got funded as part of the National AI Research Resource, where we are trying to see whether we can use, in addition to prompting, these ontological structures, these knowledge models, for optimizing the fine-tuning of language models for niche applications. And with that, I'll stop with acknowledgements. We have Katrina, Deepak, and Pedram here. There are many other undergraduate and a new PhD student, Tom, who have joined our lab, and I'd like to also acknowledge all the collaborators as well as funding agency. I'll stop here. Thank you.
That's it. So, guys, any questions?
I have a question.
Yeah, go ahead. Come,
Yes.
maybe just come closer here. I think. Right.
Am I audible, sir?
Yes, yes, I can hear you.
Yeah. So the 9 categories that you had mentioned in the initial part of the slides. So, for instance, if in future studies there was a new category introduced into the study that needed to be assessed, so how would you predict it would, how would it affect the ontology augmented prompting? Since there is not a lot of data related to that category, since it is newly discovered, uh, could you cover like could you
So that's a good question. I would try to answer it along two axes. One is, of course, does the ontology have the terms, first of all, right? If it's something new that has been discovered, then that brings up the problem of expanding the ontology. And this ontology has been iteratively expanded over the last 15 years, as I mentioned. So that's number one. Number two, that's the easier problem. So for Pedram to modify his pipeline to integrate the expanded ontology with the new information, new dimension, for example, and augment the prompt expression, maybe even edit the prompt expression corresponding to that new dimension and extract the information. Of course, I should mention here, in addition to text, Pedram is also working with actual experimental data from our collaborators. So these are Excel spreadsheets from studies being done. We are trying to integrate that into our knowledge space for these models. Does that answer your question?
yes it does. Thank you.
So I have one question actually. My name is Venkat and I'm Dr. Shit's student actually. I'm also working in active research, creating the custom AI model, not a large language model, but being more towards the small language model. The one thing that you mentioned, because I'm trying to use knowledge graph both in the training, the pre-training of the LLM, language model, and during the inferencing side of things like that. That's when I was more, when you say about augmented ontology augmented prompting, I was a little bit excited about it because I wanted to use knowledge graph both in the training as well as in the LLM in the inferencing side of things. But I think Bedram is the one person who is working in your area. Probably I would like to work with Bedram more in detail about like how are we doing that ontology augmented prompting. Um, so yeah,
Sure,
that's all.
sure.
I think you want to.
Sure, happy to. Pedram is all of I would say Deepak and Katrina and Pedram are highly collaborative. In effect, they go over to the hospitals see nearby as well as reach out to our clinicians all the time. And yeah, please feel free to shoot an email to any one of them and start interacting with them. Yeah, please.
Just a follow-up question on that, right? So, for example, right now, people have tried. I mean, I know the prompt engineering is also an evolving area, but people trying to do with few shot learning or single shot learning and things like that, so that they get some exciting results. But sometimes it fails as well. But when you say the ontology augmented prompting, which gives you the 100% of accuracy, that's a great learning that probably that we can use it for like enterprise AI use cases or things like that, because there also we have like kind of an ontology if it is a supply chain or healthcare or related things like that. That's a new learning there. Thank you for
Yes,
sharing that.
yes, sure. Yeah, the only caveat, of course, is you have to put in the time and effort to create high quality knowledge models. Once you have that, it's a one-time investment, but it pays off in multiple different ways and over the long term. That's the take-home message. If I had one take-home message, that is it. That there's a great return on investment with a knowledge model.
But with the LLM, I think that one good use of LLM is that we can use a large language model to get the skeleton or scaffolding of that ontology, and then a human expertise or an expert in that field can go back and rectify that. Instead of taking 5 hours, it can take 30 minutes to really do it.
Yes, you are on the correct path. So a long time ago, Christopher Thomas, a Dr. student, had talked about this approach long time ago. So maybe you can have a look at Chris Thomas's thesis. So yes, automated ways of creating a scaffolding from text. Yeah, it's an important approach and an interesting aspect.
Satya, you know about obviously in your time frame, your PhD time frame, people use Protege for ontology design. Now we have created an equivalent of today's knowledge graph development platform called Empower,
Oh, okay.
and it's a very comprehensive platform that will take unstructured, semi-structured, and structured data sources to help you create knowledge graphs. And this can be a very large knowledge graph. We created one for pharma domain that has 3 million entities and fairly large sort of knowledge graph that are created with a very large degree of automation. It all comes down to later on curating to ensure that quality is correct, good. Otherwise, now very scalable development of knowledge graphs is becoming possible, and then with that knowledge graph, you can, that is your knowledge representation from which you can complement the symbolic part of a neurosymbolic approach.
Yes, we'll look it up. We'll look up
Yeah.
this tool, definitely.
And there are also labs and tutorials available on how to use them, and there's a page on which you can directly play with it.
Yeah.
It also is more professional grade. It's not a toy, so it's usable, practical. Okay, great guys.
Okay.
I hope